Today's episode of the Gone Fission Nuclear Report is brought to you by Fluor. We're building a better world. Welcome to the Gone Fission Nuclear Report, your one-stop source for all the latest news from the Department of Energy's Environmental Management Program. Now, here's your host, Michael Butler.
Hello, and welcome to the Gone Fission Nuclear Report. Today is Monday, March 27th, 2023. We're covering all the news from the Department of Energy's Environmental Management Program across the country. We thank our friends at Fluor for being presenting sponsor for today's episode. DOE's Savannah River site has 51 underground storage tanks located in 2 tank farms. These tanks were built to hold radioactive liquid waste from Cold War-era nuclear weapons production. 8 of the tanks have been emptied and closed, cleaned out, and filled with grout to permanently remove them from service. The remaining 43 tanks contain about 34 million gallons of liquid waste. Each of the tanks contains 2 types of waste, salt and sludge. The sludge is processed through the Defense Waste Processing Facility. It's vitrified or mobilized in glass and placed in specialized containers to await transport to a future nuclear waste repository. The salt is processed through the Salt Waste Processing Facility. The low-level portion, called decontaminated salt solution, is sent to the Saltstone production facility, which acts as a giant concrete plant and mixes the waste with a concrete-like substance for disposal in Saltstone Disposal Units. These units are central to the waste disposal mission. Here's DOE Federal Project Coordinator Charles Comeau talking about the critical role these units, called SDUs, play in mission success.
So for the salt waste processing facility to operate, they have to have somewhere to send the decontaminated salt solution. They send that to Saltstone production facility, but we only have a limited storage capacity at the Saltstone production facility for what we call the decontaminated salt solution, the DSS, that comes from salt waste. So if there's not room at Saltstone production facility for the DSS, salt waste cannot operate. Now, Salt Waste Processing Facility came online a couple of years ago, and they have been ramping up. It's a new facility, and they're hitting their goals now for production, which means that we have to hit our goals for having storage capacity, which is the Saltstone Disposal Units. So at Saltstone Production Facility, they have to have somewhere to send the grout, and the SDUs are the final link in that chain. So without the SDUs, without that storage capacity, Saltstone production facility cannot run, and then salt waste can't run. So it's all integrated together and all has to work in harmony for the operation to succeed.
We'll have more on the SRS liquid waste mission later in the podcast. And we'll have today's headlines after this from Fluor. Idaho National Laboratory has completed a major cleanup milestone, transferring thousands of spent fuel assemblies from wet storage to dry storage at the Idaho Nuclear Technology and Engineering Center. Crews completed the 1995 Idaho Settlement Agreement milestone more than 9 months ahead of schedule. Some of the fuel was from the 3 Mile Island Unit 2, and some from the experimental breeder reactor. The now empty spent nuclear fuel storage basin, the largest in the world, will remain open until EM and the Idaho Environmental Coalition complete the remaining mission work. DOE will determine the final end state for the basin at that time. EM Senior Advisor Ike White, Idaho Governor Brad Little, and other dignitaries will recognize the achievements of employees and the safe completion of the milestone tomorrow at the Idaho Nuclear Technology and Engineering Center. Representatives from the Japan Nuclear Damage Compensation and Decommissioning Facilitation Corporation, or NDF, visited EM headquarters in Washington and the Hanford site in Washington State recently. The visit was intended to promote collaboration and provide updates on the status and plans to decommission Tokyo Electric Power Company's Fukushima nuclear power station. An earthquake on March 11, 2011, caused unprecedented nuclear damage to the station and surrounding communities. The NDF was created following the disaster to oversee the decommissioning and cleanup of the station. Now let's take a further look at the SRS waste disposal process and the key role Saltstone Disposal Units play in the mission's success. This is one of the best descriptions of waste treatment I've seen. I hope you like it.
The mission is to treat the waste and close the high-activity radioactive waste tanks at the Savannah River site. Part of the liquid waste system supports continued chemical separations operations of H Canyon. However, the majority of the highly radioactive waste is a legacy of nuclear weapons production created during the Cold War. About 34 million gallons of this radioactive waste are now stored in numerous underground carbon steel tanks at SRS. The waste has millions of curies of radioactivity and requires permanent isolation from the environment. The radioactive waste is primarily in two forms, sludge and salt. The sludge makes up less than 8% of the waste volume, but contains nearly half of the curies, or amount of radioactivity. The remainder of the waste is in the form of salt, which is about 92% of the volume and approximately half of the radioactivity. Two key facilities safely treat and dispose of the salt and sludge wastes: the Salt Waste Processing Facility and the Defense Waste Processing Facility. The Salt Waste Processing Facility, or SWPF, is treating the salt portion of the waste. It began operating in 2021. The salt waste undergoes a two-step decontamination process at SWPF. The first step removes strontium and long-lived actinides from the salt waste through the process of absorption. The second step removes the radioactive cesium by extraction. This part of the SWPF process uses a special solvent and over 30 centrifugal contactors to mix and separate the solutions. Both the absorbed waste and the extracted cesium solution are transferred to the Defense Waste Processing Facility, or DWPF, and combined with the sludge waste for vitrification. Then the remaining salt solution that has been decontaminated is ready for treatment and final disposal at the Saltstone production facility. Saltstone is produced by adding dry grout feeds to the decontaminated salt solution. This grout solution is then pumped to an engineered state-permitted unit called a Saltstone Disposal Unit, where it hardens to form a final disposition form. The Saltstone Disposal Units, or SDUs, are a critical part of the liquid waste system, as they are permanent disposal units that will hold solidified decontaminated salt solution at SRS. 3 megavolume SDUs have been built at SRS, and several more are under construction. The large-scale units can hold 33 million gallons, equivalent to the amount of water that would fill 55 Olympic-sized swimming pools. DWPF is treating the sludge portion of the waste. It began operating in 1996. DWPF converts the highly radioactive portion of the liquid waste, the sludge, into a solid glass form suitable for safe, long-term storage. Scientists have long considered this glassification process, called vitrification, as the preferred option for treating long-lived radioactive waste. To turn waste into glass, a sand-like borosilicate glass called frit is mixed with the waste and sent to the plant's 75-ton steel and ceramic melter. In the melter, the waste frit mixture is heated to nearly 2100 degrees Fahrenheit until molten. This molten glass waste mixture is then poured in a pencil-thin stream into stainless steel canisters to cool and harden. Each canister is 10 feet tall and 2 feet in diameter. Typically, it takes a little over a day to fill one canister. A filled DWPF canister weighs about 5,000 pounds. After a canister is filled, the exterior is blasted with a frit water mixture to remove contamination. A stainless steel plug is fitted into the neck of each filled canister, and the canister is welded shut using a current of 250,000 amps applied for 1.5 seconds, while 80,000 pounds of force simultaneously rams the plug into the neck of the canister. The resulting weld is as strong as the 3/8-inch thick stainless steel canister itself. More than 4,300 canisters have been filled at DWPF since it began operating. A specially designed shielded canister transporter moves each sealed canister one at a time from DWPF to interim storage buildings adjacent to the facility. At the storage buildings, canisters are lowered by the transporter into seismically qualified underground reinforced concrete vaults. The storage buildings are being modified to double the capacity by stacking 2 canisters in each storage position, exceeding the total number of canisters projected to be produced by DWPF. Double stacking canisters instead of building another storage facility saves at least $100 million in taxpayers' money. The canisters will be safely stored at SRS until a federal repository is established. Once the salt and sludge are removed from the waste tanks, final tank cleaning and operational closure can begin. The tanks are first cleaned to ensure they meet the long-term closure objectives. Next, the tanks are isolated from the liquid waste system by deactivating transfer paths and disconnecting normal services. A specifically formulated grout is then poured into the cleaned underground tanks. The grout binds residual radioactivity and finalizes the closure process. It's the goal of Savannah River mission completion to safely remove the waste and close the remaining waste tanks by the year 2037. Until then, all the liquid waste facilities will continue to work together as an integrated and interconnected system. By executing the mission, the liquid waste team at the Savannah River site reduces radiological risks to employees, surrounding communities, and the environment, ensuring a safer future for everyone.
We'll be back with this week's Spotlight interview right after this from Fluor. Now it's time for this week's Spotlight interview. We've noted that Saltstone Disposal Units are central to the waste disposal mission. Today's guest, Charles Comeau, Federal Project Director for Saltstone Disposal Units at the Savannah River site, sheds more light on the importance of these units in this week's Spotlight interview. We're talking with Charles Comeau, who's the Federal Projects Director for the SDU Saltstone Disposal Unit project at the Savannah River site. Hello, Charles, and welcome to the podcast.
Thank you. I'm glad to be here.
The Saltstone Disposal Unit is the ultimate home for this grouted saltstone material. Now you have, I think you have 12 saltstone disposal units in your project right now, and they vary in size. Can you take us back to kind of the start? I understand the first one may have been built around 1986, and they've evolved over that time in terms of their size and their capability. Can you kind of take us through that? What's happened with the development of the units over time?
Sure, no problem. So the Saltstone disposal units are above ground tanks that are designed to hold the saltstone grout. The original tanks or saltstone disposal units that we constructed were two of those, and they were rectangular in shape. And we found that those did not work well because the hydrostatic pressure exerted on the sides of those structures. The sides tended to want to bow outward and crack. And being made from concrete, that didn't work well. So it was not good for containing the liquid form of the saltstone before it hardened. So the next evolution of the saltstone disposal unit was based on an American Water Works Association design above ground water storage tank. We moved to that design, and that worked very well for us because it's designed for the hydrostatic head that exists inside the tank. However, the second evolution or second generation of tank was only 3 million gallons in size. And when we started looking at the volume of storage that was going to be needed, we realized we'd have to build over 80 of those small diameter saltstone disposal units, and we didn't really have the space to build them in our landfill area. So we went back and we looked at optimizing the size, and we came up with what we're building now, which is the third iteration, which is the mega SDU, we call it, which has 34 million gallon storage capacity. It's 375 foot in diameter and 43 feet high. It too is based on an American Water Works Association design for an above ground water storage tank, but we've modified that design to fit our need. And it started with what we call SDU6, and SDU6 and SDU7, those have been constructed and are in operation. SDU8 is the third mega SDU. It is nearing completion and will be put into production later this year. SDU9 will be put into production about a year after that. And then SDUs 10, 11, and 12, that project is getting underway. We have completed site preparation on SDU 10, and we'll be starting the cell construction later this year. And then following that will be SDUs 11 and 12. And once we complete SDU 12, that will complete that provide us with all the volume we need for saltstone disposal through the life of the liquid waste program.
Well, these are major construction projects. The latest ones that you're building have 10 times the capacity of the earlier ones, with 33 or 34 million gallons that you're able to store in there. So, and you're in charge of the construction on behalf of DOE. Can you talk a little bit about what goes into building an SDU?
Sure. Well, it all starts with exploring the ground where we're going to put it. We do geotechnical investigation and get a good feel for what's under the ground before we start, to make sure that the location is adequate and we're not going to have any subsurface issues. Once we have the geotechnical, we design the tank itself for those geologic conditions. And then we excavate down. We do the site preparation. So we excavate down to set the tank below the existing grade, because at the end of the mission, all these SDUs will be covered with an earthen cap. And so we don't want them too high in the air, because we want them down as low as we can get them, as deep in the ground as we can get them to start, because we're going to need a lot of fill at the end to cover the entire saltstone disposal facility with that cap. So we excavate down, get down to the elevation where we need to be, and then we put in subsurface drains to control rainwater, since we're below grade. And then we start putting in mud mats. We put in a lower mud mat, and then we put in a geotechnical clay liner with an HDPE liner. and then we put another mud mat on top of that. And the reason for that HDPE GCLE liner system is at the end, that acts as a leak detection, leak collection system. If there were to be a leak out of the SDU, it would be collected there and go into a sump. So that's a feature that we have as a backup to make sure that nothing gets out of these tanks as we're filling them and while the material is hardening. So then we move to the foundation of the tank. It's 2 foot thick reinforced concrete, and again 375 foot in diameter. So we place that in multiple sections, and then we start putting up the walls. There are 25 separate wall panels that go into making the SDU. Those walls are 2 foot thick as well, and at the bottom, 12 foot inches at top, so they're tapered because of the hydrostatic pressure. You need thicker concrete at the bottom. Once the walls and the floor are going up, then we start putting in the columns. Columns are 2 foot diameter, and they are 208 columns, and those are there to support the roof, which is also going to be a concrete slab. So we get the walls in place. After the floor is done, we get the columns in and we start placing the roof. And once the roof is complete, the cell structure is complete, then we wrap the tank with over 300 miles of steel cable under tension. So we post-tension the walls in compression to counteract the hydrostatic pressure that's going to be encountered when we fill the tank. And then we also cover the wire wrapping with shotcrete to protect it. So once that is complete, the cell is complete at that point. Then we go inside the cell and we rubber line it from the floor and the walls get rubber lined. And this is another barrier against leakage because concrete is very difficult to construct where we have a very tight tolerance of zero leakage out of these tanks. And being concrete, it's very difficult to build a concrete tank that would have zero, and I mean zero leakage. So we do the rubber lining, completely line the interior of the tank, and then to check for leakage, we fill the tank all the way up with water. We add a fluorescent dye, and then we let it sit for 3 days. And at the end of the 3 days, we do a black light inspection on the exterior of the tank to see if there's any leakage. And that's how we ensure that there's absolutely zero leakage when the tank is complete. Once that test passes, then we drain the tank, we clean it out, we do one last inspection, and then we close it up. And the cell itself is complete. And at that point, then it's just a matter of completing what we call the balance of plant, which is tying the tank into the Saltstone production facility with all the piping and controls. And once all of that is done, we do a readiness assessment of the tank, make sure it's ready to go, and then we turn it over to operations. And they start placing grout into the tank.
Well, this is obviously a highly engineered, very sophisticated construction that speaks to the safety of the storage. Can you talk about that a little bit in terms of safety? Once this grout goes in there, it's not going to be going anywhere after that, is it?
No, it's not. So the whole thing with you're talking about radioactive materials and radioactive waste, you want to keep it out of the environment. You want to keep it out of the water, you want to keep it out of the air, and you want to prevent exposure to human beings. So placing this in the grout form, it becomes a non-hazardous material. And it will sit there and it will decay over thousands of years. But it's not going to, it cannot get back into the water supply as a liquid, and it cannot get into the air. Again, once all these tanks are filled and liquid waste mission is complete, the entire area will be covered with an earthen cap and a liner system to divert water away from it. So that's the final disposition for this fraction of the waste. The waste that went to DWPF or Defense Waste Processing Facility, that waste goes into glass, and that gets put into stainless steel cylinders, which will then go to a long-term repository somewhere. It was going to be at one point Yucca Mountain, but Yucca Mountain has been, it's not happening. So We don't know where it'll go, but at some point there will be a place for the high-level waste canisters to go off-site and to be stored permanently.
Well, by going to these mega volume SDUs, you were able to, that represents a savings as well, right? Because of the
Yes.
economies of scale, it helps to keep the cost down in the disposal of the waste.
When we did the analysis and made the decision to go to the mega SDUs at that time, which is now coming up on almost 10 years, we were saving $2.25 a gallon for each gallon of waste disposed. So if you extrapolate that out and you escalate it for time, it's a big, huge savings. It's a huge savings for us in cost.
The completion of these SDUs is a very high priority for environmental management. It's on the list, high on the list of the 2023 and ongoing priorities for the department. And the reason for that, I believe, is to be able to keep up with the production capacity of the SWPF. What SWPF seems to be really on a very high operating capacity right now. What tell us about that and the role that the SDUs play in making sure that the operation can continue efficiently going forward?
Sure, no problem. So for the salt waste processing facility to operate, they have to have somewhere to send the decontaminated salt solution. They send that to Saltstone production facility, but we only have a limited storage capacity at the Saltstone production facility for what we call the decontaminated salt solution, the DSS, that comes from salt waste. So if there's not room at Saltstone production facility for the DSS, salt waste cannot operate. Now, salt waste processing facility came online a couple of years ago, and they have been ramping up. It's a new facility, and they're hitting their goals now for production, which means that we have to hit our goals for having storage capacity, which is the Saltstone Disposal Units. So at Saltstone production facility, they have to have somewhere to send the grout, and the SDUs are the final link in that chain. So without the SDUs, without that storage capacity, Saltstone production facility cannot run, and then salt waste can't run. So it's all integrated together and all has to work in harmony for the operation to succeed.
Other sites in the DOE complex are looking, I'm thinking about Hanford, are looking at decades of work to finish their liquid waste mission. What is the time horizon at Savannah River? How much longer do you think it'll be before you're through with the waste tank work there?
We have set a goal to be complete with the liquid waste mission in 14 years. So that puts us out to around 2038, FY 2038, to be done with the liquid waste mission here.
Okay. Is there any, we've talked about quite a few things here related to the SDUs and the tank waste mission. Is there anything else that you'd like for us to know, our viewers and listeners to know, that we haven't covered in our discussion so far?
Well, we're very proud of the success we've had here. We've been building these mega SDUs now for almost 10 years, and we completed all of the SDU projects so far. SDU 6 was the first project. We completed it ahead of schedule by more than a year and well under budget. SDU 7, again, we completed it well ahead of schedule and under budget. SDUs 8 and 9 are coming in ahead of schedule and under budget. So we're very proud of our track record, and we appreciate the support that we've received from headquarters. They get us the funding, and we get the job done. We get the projects completed, and we get them done on time, and we get them done within cost. So we're happy with our progress to date, and we look forward to completing this mission ahead of schedule and under cost, hopefully.
Well, Charles, you and your team are doing outstanding work, and we really appreciate you joining us on the podcast today.
I'm glad to be here, and I appreciate you taking time to speak with us.
Today's episode of the Gone Fission Nuclear Report is brought to you by Fluor. We're building a better world.